So today we're going to talk about the exponential growth. Exponential growth. Okay. So what is exponential growth? That is a type of growth that's not linear. If we have a graph here, we can think of something that grows linearly, would grow like that. Okay. It has a slope. It has a rise over a run, right? And if we think of this as X here and Y, for every one you go over, you go up two. I'm sorry, for every two you go over, I guess this would be three, and this would be two there because it's got to go over two. For every two you go over, you go up one. Okay. And that would be, it's the same difference between each step. Exponential growth is a little bit different. Exponential growth at the very beginning of the growth is very small, almost unnoticeable. But then as time goes on, it gets to be massive. Okay, it kind of has a curve to it. And with every passing number on the x axis, y gets increasingly and increasingly higher. Okay, so let's take a real practical example that all of us will engage in. Let's say that you are able to save some money. Okay, let's say you went and you made $100 mowing a few lawns. Okay. And you say, you know what? I'm going to take that $100 and I'm going to invest it in, let's say, the bank. Now, I'm going to use 10%, but that might not be realistic, but at least to show you how the percentages work. So let's say that you go to the bank and say, hey, I'd like to open an account. And the account says that your money in there every year, it'll increase by 10%. Okay. So every year, however much money you've had in the bank for the whole year, $100, it'll go up by 10%. Okay. So let's think about this. Your initial investment or year zero, okay, is $100. After 1 year, all right, after 1 year, we're going to add 10% to this. So you take your initial amount of money, and then I'm going to add 10% of, and remember, of is multiply $100. Okay. So this is 100 plus 10% is 0.1. Of is multiply, and 100 is 100. Okay, so 0.1 times 100 is 10. So this is 100 plus 10. So at the end of year one, your bank account will have $110. All right, now let's say that we just leave this alone, okay? So we just leave that alone. We go into year two. At the beginning of year two, I have $110. And then at the end of year two, it's going to go ahead and increase that by 10%. So that's 0.1 times however much is in there. So that's 110. Okay, oops, it's supposed to be a plus. So $110 is what was in there at the end of year one, beginning of year two. And now at the end of year two, we're going to add another 10%. So 0.1 of 110 is 11. So we add those two numbers together, we get $121. So we can see that from an initial investment of $100, just leaving it in the bank at a 10% year return gives us $121 at the end of year 2. All right, so let's go to year 3. We start the year with 121. We are going to add 10% of 121. So this is 121 plus $12.10. 121 plus $12.10 will be 133.10. Okay. And this is what we call exponential growth. Okay, if we were to sort of graph this on a table, okay, we'd say at year 0, we'd have $100, okay, at year 1, year 2, and year 3. So we'll say up here is 200. Here's about 150. Okay, so we get about 110 after the first year. Okay, we'll do this in a different color to kind of show the difference here. The second year at 120. Third year at about 130. 30. So it's not necessarily noticeable in the first 3 years, but there is some curve to it. And I know there is because the distance here, all right, between 100 and 110 is 10. But the distance here between 110 and 121 is 11. And then the difference between 121 and 133.10 is 12.10. So you can see that this is not a straight line. We are getting some curve. And in fact, if we go out there year over year, this distance between what's inside the account at the beginning of the year versus the end of the year is going to get drastically higher and higher. This is one of the reasons why it's such a good idea to invest money early and allow that money to compound over time. Okay, so let's go back to our equations here where we were looking at exponential growth. And let's kind of draw some generalities here. So if we look at the initial investment, we're going to denote that with the letter A because I want to be able to basically kind of have a generic equation that I use to predict in the future. If I know that I get 10% every year, then I should be able to come up with an equation that I could say, okay, well, let me figure out if I just let that grow, how much money is in there after 18 years? You know, if somebody's born and I put $100 into an account and just let it grow for 18 years when they graduate high school, how much money does that give them? So let's go here and let's do some generalizing. What I mean by that is our initial investment, we're going to say, hey, that's just A. Okay. And that's going to be for year 0. Okay, that's just A. Now let's go to year 1. Okay, year 1 is going to be our initial investment, in this case 100 or whatever it is, plus the percent it's going to grow times that investment. Okay, times this number. So we can write that for year 1, it's A plus 10%, and I'm going to use the letter R to denote rate. Okay. So over here, let me define my terms. A is initial investment. R is rate. Okay. Okay, and that gives me the amount in year one. Sorry. 10%, not just the rate of 100. So times whatever the amount is that I invested, which was that A. Okay. So if I were to do that, 100 plus zero point 0.1 times 100, that gives me 110. This is the new amount at the beginning of year two. This is the new amount. How did I get that? 100 plus zero point 0.1 times 100. So here, for year two, I'm going to start with what was the end of year one, which is this number right here. Okay. Okay. Then I'm going to add 10% of that number. So I can add plus 10%, or in this case, my rate of that same number. Okay. Now I want to notice a few things. We're going to simplify this. And the first thing I notice is here I have like common factors in both um, terms here. So I can pull the A out, and this becomes A. And then if I pull the A out of here, that becomes 1. And then I can add R times A. I pull the A out. I'm just left with R. Okay. Now here, this is similar. I'm going to pull the A out. 1 plus R. Plus, then here I have my R. And then here I have the same thing, just like I do here. So I'll pull that A out. And I have 1 plus R. Now you'll notice that A and 1 plus R exist in both terms. So I can now pull that out. So I pull the A out, it gives me A, and then I pull the 1 plus R out. And what's left? If I pull out A times 1 plus R out, what's left here is just the number 1. Because A times 1 plus R times 1 gives me A times 1 plus R. If I pull the A times the quantity 1 plus R here, what I'm left with is that R. So here we see that at the end of year 2, or at the end of year 0, which is when you first start, I have A. At the end of year 1, I have A times 1 plus R. At the end of year 2, I have A times 1 plus R times 1 plus R. Okay, so what about year 3? Let's take this another step further. So here in year 3, this is the final amount that exists in at the end of year 2 is what is at the beginning of year 3 and what I take the 10% of. So at the end of year 2, that's this number right here. Okay. So for year 3, I have A times 1 plus R times 1 plus r. That is my 121. Plus, okay, so for year 3, and I'm going to add the rate, 0.1. That's my rate. In this case, 0.1. And my initial investment, in this case, 100. Here, my rate times that 121, which is this number. A times 1 plus r times 1 plus r. Okay. Now, we can notice something similar. We have a 1 plus r, 1 plus r, and a 1 plus r, 1 plus r. I can, that's, and here's my plus term, or my plus operation. So I've got common factors. I can factor all that out. I can factor the a out of both, the 1 plus r out of both, and the 1 plus r out of both. So if I do that, 1 plus r, 1 plus r. Okay, I've factored that out. What I'm left with, if I factor out of this, the a times 1 plus r times 1 plus r, what I'm left with is a 1, because this times 1 would give me that back, plus, and then I'd have my r over here. This times r is what we have right here, this times r. But notice how that adds another 1 plus r. So at the end of year 3, my number is a times 1 plus r times 1 plus r times 1 plus r. Now, I go through all that so that I can show you, this is not a formal proof, but what it does show us is that depending on how many years, that's how many times I'm multiplying the factor r plus 1. So here it's once, here it's twice, that's year 2. Once was year 1. And over here for year 3, we're multiplying that 1 plus r 3 times. Now, even for year 0, we could say that this is 1 plus r, and then we could multiply this 0 times, which just gives us 1. So that would be, in other words, if I raise this to the 0 power. So what this tells us is I multiply the factor 1 plus r for however many years. Okay, so let's make x. Sometimes people will use t, that makes more sense. But just so that we understand how it goes on the graph, x is the number of years. So this is what the equation would look like. Generically, the amount that we're getting, or y, okay, if we go back to our graph, y would be the amount of money that we're getting, 100, 110, 121, 133, 10, okay, is equal to the initial amount of money that you put in the bank times the quantity, 1 plus the rate, and I'm going to multiply this 1 plus the rate times however many years. So if I'm looking at year 3, I'm going to look at multiplying that 3 times. That x right here is going to be 3, right? The x here is going to be 3. So now let's look. How much would I have in year 18? Well, if I take the same idea, so I'm going to start with $100. It's going to grow by a rate of 10%, or 0.1. And I'm going to look at that after 18 years. Okay. All right. So this would be 100. 1 plus 0.1 would be 1.1 to the 18th power. Okay. So I'm going to use my calculator to do this. Give me just a second here. Oh, there we go. Okay. So we'll do 1.1 raised to the 18th power. Okay. Now I'm going to take that number, which is 5.55991, and I'm going to multiply that by $100. All right. So that initial investment of $100 in 18-year grows to $555.99. And that is a lot easier to calculate than figuring out after every year what my final value is. So now that we kind of understand where this comes from, okay, we can work a few problems that are going to be on your homework. All right, so let me get it pulled up here. All right. So it says that rentals in a high-rise apartment building get more expensive the higher up you go in the apartment building. And the reason for that is that the views are nicer. So if you can think about an apartment building, it's going to be the most affordable down on the first level and the most expensive at the top. Okay. The ground floor, or floor 0, that rent is $1,660 a month. Okay. Now, for every floor you go up, the price increases by 3%. Okay. How much is rent on the 9th floor? Okay. Okay. How much is rent on the 9th floor? Okay. So what we want to do here is we're going to look at our exponential increase formula that we derived, and there is a formal proof for this, but we're not going to worry about that at this level. But you know enough to know that this is going to give you the information. This is going to yield the value that you're looking for. All right. So what is our initial value? That's right here. We could think of this as floor 0. This is floor 1, 2, 3, 4, 5, so on and so forth until we get to floor 9. Okay, so our initial is 1,660. That is my A value. 1,660. All right, my rate, or R, by how much does it go up, is 3%. and it goes up for every floor. Okay, so this X is no longer time. We're not looking at how much more money do I have at the end of 18 years. We're looking at how much more money does this cost at the top of 9 floors. So it raises 3% every floor, and we're going to look at what happens at the 9th floor. Okay? All right. So we'll plug this into our equation. All right. And I look at 1.03 raised to the 9th power times 1,660, and I get 2,165.92. That's how much rent is going to be on the 9th floor.